Hey guys, tonight we're going to dim the lights and observe a cosmic culinary event of truly unimaginable scale. Not the gentle dance of planets or the slow fusion within a star, but a silent, violent, and ultimately inevitable confrontation between a star and the ultimate predator of the cosmos. We're talking about black holes, not just as static gravitational traps, but as active, hungry entities, and the gruesome reality of what happens when they decide to feed. We're delving into the inevitable feast when black holes consume stars. Maybe turn on a fan for that soft background hum. And let's ease into tonight's truly chilling, profoundly destructive, and ultimately profoundly unsettling journey together. So, welcome to the cosmic dining table. Often romanticized as rare, spectacular events seen only in distant galaxies. Forget the grand fireworks and the comforting distance. Forget the very notion of a fair fight or a chance of escape. Everything you know about a star's longevity, about its stability, about its very existence, is utterly, fatally useless here. Here tonight, we're going to peel back the layers of cosmic drama and settle into the unvarnished, profoundly uncomfortable truth. You see, the reality is, if you woke up tomorrow, right now, just as you are, a star too close to a black hole, you wouldn't survive a single millisecond. Your very atomic bonds would unravel. But let's imagine, for a moment, that you could somehow exist and perceive this silent, horrific consumption. The true story of a star's demise at the hands of a black hole is one of immense power, unimaginable stretching, and a complete, terrifying loss of identity. Before you get comfortable, take a moment to like this video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights. Congratulations, you've just woken up, suspended in a black, infinite expanse of deep space, with a front row seat to a stellar execution. The good news, you're alive. For now, the bad news, you are utterly helpless in the most spectacular event before you will unfold in absolute, profound silence. The very first concept we must truly absorb tonight is that while black holes are often portrayed as vacuum cleaners of the universe, indiscriminately sucking up everything in their path, this isn't strictly true. They have a gravitational pull, yes, but objects can orbit them safely, just as planets orbit a star. The danger arises when an object, usually a star, gets too close. This too close isn't just about distance, it's about crossing an invisible boundary where the black hole's differential gravitational pull becomes overwhelming. This specific phenomena is known as a tidal disruption event, or TDE. It's a stellar catastrophe, a celestial horror story unfolding in the silence of the void. Imagine a star, much like our sun, perhaps quietly orbiting the supermassive black hole at the center of its galaxy. Most stars in a galaxy are far enough away to be perfectly safe, living out their lives for billions of years. But sometimes, through gravitational interactions with other stars, or perhaps just a very unlucky trajectory, a star finds itself on a path that brings it dangerously close to the black hole's event horizon. This is the beginning of the feast. As the star approaches the black hole, it enters a region where the gravitational pull becomes incredibly strong. But it's not just the strength of the gravity that matters, it's the difference in gravity across the star's body. The side of the star closer to the black hole experiences a much stronger gravitational pull than the side farther away. This differential force is what we call a tidal force, and it's the same phenomenon that causes tides on Earth due to the moon's gravity, just amplified to an unimaginable, destructive degree. This stretching is silent. There's no sound of groaning stellar material, no audible tearing of hydrogen and helium, just the relentless, invisible hand of gravity pulling more strongly on one side than the other, silently deforming the star. The internal pressures and forces within the star which have maintained its integrity for millions or billions of years, are now utterly overwhelmed by an external force that increases exponentially with proximity. As the star gets even closer, the tidal forces intensify beyond anything we can easily comprehend. The star's very molecular bonds, its atomic structure, the forces holding it together, begin to fail. The material on the side closest to the black hole is pulled with such ferocity that it begins to detach from the rest of the star, creating a long, thin stream of gas and plasma. This is the initial stage of destruction, a quiet, inexorable unraveling. This silent approach, this slow but inevitable distortion, highlights the terrifying power of black holes. They don't need to collide with something to destroy it. Their mere gravitational presence is enough. The star, helpless in its orbital death spiral, is already condemned, its fate sealed by its trajectory in the unyielding laws of cosmic mechanics. It's a slow-motion, silent ballet of destruction, playing out over hours or days, where the star is silently being stretched and pulled apart, molecule by molecule, before any material even crosses the event horizon. And then, the moment of ultimate destruction arrives. When the star crosses a critical boundary, known as the tidal disruption radius, the black hole's tidal forces completely overcome the star's own self-gravity. At this point, the star is utterly torn apart. It doesn't explode in a nuclear sense. It's gravitationally shredded, literally ripped to ribbons of gas. The stellar material, previously contained within a distinct star, is now a long, thin stream of superheated plasma, stretched out along the black hole's gravitational field, forming what scientists call a stream of stellar debris. This is spaghettification on a stellar scale, a complete cosmic unmaking. This stream of material doesn't just disappear. Roughly half of the star's shredded material is flung outwards into space, sometimes at speeds approaching 10,000 kilometers per second. Silent, violent expulsion of stellar guts into the void. This ejected material will eventually cool and dissipate, perhaps one day forming new clouds of gas and dust far away. The other half of the star's material, however, remains gravitationally bound to the black hole. This material doesn't just fall straight in. Instead, it orbits the black hole, slowly spiraling inward, forming a vast, flat, superheated structure called an accretion disk. Imagine a colossal cosmic drain where stellar gas swirls faster and faster, generating immense friction and heat as it compacts. This disk glows with unbelievable intensity, reaching temperatures of millions, even billions of degrees Celsius. This extreme heat causes the material in the accretion disk to emit vast amounts of radiation across the electromagnetic spectrum, especially in X-rays and gamma rays. This is the flare that accompanies a tidal disruption event, making these otherwise invisible cosmic feasts observable to our telescopes across vast cosmic distances. For a brief period, perhaps months or even years, the region around the black hole becomes incredibly bright, radiating more energy than an entire galaxy, all powered by the slow, frictional death spiral of stellar material. This light, though blindingly bright, is not accompanied by any sound. No sizzle, no hiss, no roar from the superheated plasma. Just a silent, brilliant outpouring of energy as the black hole continues its meal. Sometimes, a portion of the material from the accretion disk, instead of falling into the black hole, is ejected outwards in powerful, narrow beams, known as relativistic jets. These jets, composed of highly energetic particles, can travel at nearly the speed of light, extending for millions of light years into intergalactic space. These are the most powerful continuous phenomena in the universe, silent cosmic lighthouses born from the violent consumption of a star. Even these jets, powerful enough to influence the evolution of entire galaxies, are fundamentally silent. Their energy, their power, their destructive reals occur without a single audible tremor. After the initial flare subsides, the remaining material in the accretion disk gradually falls into the black hole. The region around the black hole returns to its previous silent darkness. The feast is over. The black hole, slightly more massive than before, resumes its quiet existence, waiting for another unsuspecting star to wander too close. These events are relatively rare in any given galaxy, occurring perhaps once every 10,000 to 100,000 years. This rarity underscores the immense patience of the cosmos, where even the most spectacular events are separated by vast stretches of time. How do we detect these events? We don't see the black hole itself, nor do we hear the star being torn apart. We detect the incredibly bright, characteristic flares of X-rays and gamma rays emitted by the superheated accretion disk. Telescopes like NASA's Chandra X-ray Observatory, or ESASXM Newton, constantly scan the skies, searching for these telltale signatures. When a new, powerful X-ray source suddenly appears in the center of a distant galaxy, it's often the telltale sign of a recent black hole feeding event. We are witnessing the last silent screams of a star, translated into blinding light millions or billions of light years away. Tidal disruption events are incredibly important for astrophysicists. They provide a unique opportunity to study the supermassive black holes at the centers of galaxies, which are otherwise very difficult to observe directly. By analyzing the light curves, the spectra of TDEs, scientists can learn about the mass and spin of the black hole, the properties of the star that was consumed, K, and the physics of accretion disks in extreme gravitational environments. They are the universe's most violent cosmic laboratories, offering fleeting glimpses into the heart of darkness. This silent, inevitable consumption highlights a brutal truth about the cosmos. Stars, vast and powerful as they are ultimately fragile in the face of truly overwhelming gravitational forces. Their lives, measured in billions of years, can end in a sudden, silent cataclysm, utterly without warning or mercy from the indifferent void. The black hole doesn't feel hunger, doesn't plan its attacks, and doesn't celebrate its victories. It simply exists, a profound warp in space-time, waiting for matter to obey its inescapable pull. On Earth, we are cushioned, protected by the delicate balance of our solar system, safe from such immediate, terrifying ends. We perceive violence through sound, through impact, through shock waves. But in the cosmos, the most profound violence unfolds in absolute stillness. Its destructive power communicated only through light that has traveled for eons to reach us. Our very existence, our quiet nights, are a testament to the immense distances that separate us from such terrifying celestial hunger. So, while the idea of a black hole consuming a star might seem like a fantastical spectacle, the reality is a brutal, unforgiving testament to the ultimate power of gravity and the silent, unyielding forces that shape our universe. It is a chilling reminder of how completely dependent we are on the stable, predictable spacetime of our own corner of the cosmos. As you drift off to sleep tonight, perhaps consider the incredible, impossible luck of waking up on a world where stars shine, predictably, where gravity is benevolent, and where the universe's most profound acts of destruction happen in absolute, terrifying silence, far, far away. Good night.